voltage drop in a conductor is calculated using the formula volts equals amps times resistance times length. Here, volts represents the voltage drop, amps is the current, resistance is the conductor's resistance measured in ohms, and length is the conductor's length in feet. Power factor is a measure of how effectively electrical power is used. A power factor of 1 indicates perfect efficiency, where all the current performs useful work. Conversely, a power factor of 0 implies no real work is done. With a lower power factor, for a given current, there is a greater voltage drop. This occurs because a lower power factor signifies a larger proportion of reactive current. Reactive current doesn't contribute to actual work, it simply circulates within the circuit, leading to voltage drop. For smaller wires, their resistance is inherently higher. Even a relatively small amount of reactive current can induce a substantial voltage drop in these wires. As the power factor declines, reactive current increases, exacerbating the voltage drop. Conversely, larger wires have lower resistance. A significant amount of reactive current won't cause a drastic voltage drop in larger wires. When the power factor is decreased, the reactive current does rise, but its effect on voltage drop is less pronounced compared to smaller wires. This explains why smaller wires show a greater voltage drop at a 95% power factor than at 80%, while larger wires display the opposite behavior. Let's delve deeper into the concept of voltage drop. Voltage drop is the decrease in electrical potential along the path of a circuit. It's an inevitable consequence of current flowing through a conductor with resistance. Excessive voltage drop can cause equipment malfunction, reduced efficiency, and even damage. The acceptable level of voltage drop varies depending on the application, but standards like the National Electrical Code, or NEC, provide guidelines. Power factor plays a significant role in voltage drop calculations, especially in alternating current or AC circuits. In an AC circuit, current and voltage are not always in phase. This phase difference is quantified by the power factor, which is the cosine of the angle between voltage and current. A power factor less than 1 indicates the sum of the current is reactive, meaning it doesn't contribute to real power consumption. Reactive power is associated with inductive and capacitive loads. Inductive loads, like motors and transformers, draw lagging reactive power, while capacitive loads, like capacitors and some electronic devices, draw leading reactive power. The presence of reactive power increases the total current flowing in the circuit, which in turn increases the voltage drop. The relationship between voltage drop, current, resistance, and power factor can be expressed more precisely with the following formula: voltage drop equals current times impedance times the cosine of the angle between voltage and current, where impedance is the total opposition to current flow in an AC circuit, encompassing both resistance and reactance, and the cosine of the angle represents the power factor. From this formula, it is evident that a lower power factor results in a higher voltage drop for a given current and impedance. Now let's consider the influence of wire size on voltage drop. Larger wires have a lower resistance per unit length compared to smaller wires. This is because larger wires offer a greater cross-sectional area for current to flow, reducing the opposition to current flow. Since voltage drop is directly proportional to resistance, larger wires exhibit a lower voltage drop for the same current and length. The NEC provides tables that specify the ampacity, or current carrying capacity, of different wire sizes. Ampacity is the maximum current that a conductor can carry continuously without exceeding its temperature rating. Selecting the appropriate wire size is crucial to minimize voltage drop and ensure safe operation. When designing an electrical circuit, it's essential to calculate the expected voltage drop under worst-case conditions such as maximum load current and minimum supply voltage. If the calculated voltage drop exceeds the allowable limit, the wire size needs to be increased or other measures need to be taken to reduce the voltage drop, such as shortening the conductor length or improving the power factor. Power factor correction is a technique used to improve the power factor of an electrical system. It involves adding capacitors to the circuit to counteract the effects of inductive loads. By reducing the amount of reactive power, power factor correction lowers the total current and reduces voltage drop. Power factor correction can also improve energy efficiency and reduce electricity costs. In summary, the voltage drop in a conductor depends on several factors, including current, resistance, length, and power factor. Smaller wires have a higher resistance and are more susceptible to voltage drop, especially at lower power factors. Larger wires have a lower resistance and are less affected by power factor. Power factor correction can improve the power factor and reduce voltage drop. Proper wire sizing and voltage drop calculations are essential for designing safe and efficient electrical circuits. To recap, the interplay between wire size and power factor significantly impacts voltage drop in electrical systems. Small wires, due to their higher resistance, experience a greater voltage drop with improved or higher power factors. This seemingly counterintuitive phenomenon arises from the increased influence of reactive current in high-resistance conductors. Conversely, large wires, with their lower resistance, exhibit a reduced voltage drop at higher power factors. Understanding this relationship is crucial for electrical engineers and technicians in designing efficient and reliable power distribution systems. The formula volts equals amps times resistance times length provides a fundamental understanding of voltage drop, but in AC circuits, the power factor must also be considered. The use of appropriately sized conductors and power factor correction techniques are essential strategies for minimizing voltage drop and ensuring optimal system performance. The NEC provides guidance on conductor sizing and voltage drop limits. Understanding these concepts enables professionals to design electrical systems that meet safety standards and deliver power efficiently. Remember that voltage drop is cumulative along the length of a conductor, so it's important to consider the total length of the circuit when calculating voltage drop. Also, consider the impact of temperature on conductor resistance. Higher temperatures increase resistance, which can further increase voltage drop. In addition to conductor size and power factor correction, other techniques can be used to minimize voltage drop. These include using multiple parallel conductors, reducing the load current, and increasing the supply voltage. Multiple parallel conductors effectively increase the cross-sectional area of the conductor, reducing resistance. Reducing the load current will directly reduce the voltage drop. Increasing the supply voltage can help to compensate for voltage drop, but it's important to ensure that the equipment is rated for the higher voltage. In many industrial and commercial facilities, power quality is a major concern. Power quality refers to the characteristics of the electrical power supply, including voltage stability, frequency stability, and harmonic content. Poor power quality can lead to equipment malfunction, reduced efficiency, and increased operating costs. Voltage drop is one aspect of power quality, and it's important to address voltage drop issues to maintain optimal power quality. Harmonic distortion is another power quality issue that can affect voltage drop. Harmonics are unwanted frequencies in the electrical system that can cause increased current flow and voltage distortion. Harmonic filters can be used to reduce harmonic distortion and improve power quality. Regular monitoring of voltage drop and other power quality parameters is essential for identifying and addressing potential problems. Power quality analyzers can be used to measure voltage, current, power factor, harmonics, and other power quality parameters. The data collected from power quality analyzers can be used to identify trends, diagnose problems, and optimize system performance. In conclusion, managing voltage drop is crucial for ensuring the reliable and efficient operation of electrical systems. Understanding the factors that influence voltage drop, such as wire size, power factor, and temperature, is essential for designing and maintaining electrical systems. By implementing appropriate measures to minimize voltage drop, such as using appropriately sized conductors, correcting power factor, and reducing harmonic distortion, engineers and technicians can improve power quality and reduce operating costs. Always consult relevant electrical codes and standards when designing and installing electrical systems.